Hello there, and welcome to the Sleeping Physicist. If you're someone who likes to unwind by thinking about stars, light, and the quiet structure of the universe, you're in the right place. Tonight, we'll let our attention drift gently into real physics and real discoveries. Some of what you'll hear may sound surprising, but all of it is real. And if you enjoy these slow journeys into how the universe actually works, you're always welcome to like and subscribe. But for now, get comfortable. Let your body rest, let your thoughts wander, and let's begin. What is force made of according to quantum physics? Press your hand against a table and notice how quickly motion gives way to resistance. Pressure spreads across your skin while your muscles adjust, and the movement ends without hesitation. Nothing visible passes between your hand and the surface, yet something decisive has occurred. Energy has shifted, motion has been redirected, and a clear physical outcome has taken place. This same pattern appears everywhere. When an object is dropped, its speed increases in a steady and predictable way. When magnets approach one another, motion begins before any contact is possible. Distance does not prevent interaction. Something operates across space itself, shaping motion long before objects meet. At the scale of daily life, this feels ordinary enough to ignore. Force appears as a simple push or pull, a basic ingredient of how things move and stop. For practical purposes, that intuition works well and keeps the world manageable. Looking more closely, a quiet inconsistency emerges. Your hand never truly touches the table in any meaningful physical sense. The atoms in your skin remain separated from the atoms in the wood by measurable distance. As your hand approaches the surface, resistance increases smoothly rather than abruptly. Motion fades gradually, guided by rules that act before contact can ever occur. Under the same conditions, the same response always appears, and it appears in the same way. This consistency is where physics begins to pay attention. Whenever nature behaves reliably, explanation becomes possible rather than speculative. At this stage, force is not yet defined by theory. It is known only through its effects, which do not vary without reason. Motion changes, energy redistributes, and systems respond according to fixed constraints. Force does not announce itself as a thing moving through space. It reveals itself through the way motion adjusts when systems interact. That makes the situation sharply defined rather than abstract. Nothing visible crosses the gap between objects, yet influence is present. Contact does not occur, yet resistance is enforced. Structure must already exist before collision. This is not a philosophical puzzle. It is a physical demand created by repeated experience. Force, as first encountered, is dependable change governed by rule. Whatever its deeper origin may be, it already behaves lawfully and without exception. With that ground firmly in place, the direction forward becomes unavoidable. Reliable behavior implies underlying structure, and identifying that structure is the next necessary step. For most of history, force was treated as something simple and direct. When motion changed, it was because one object acted on another, and that action was called a force. This idea fit naturally with human experience. Push a door, and the door moves. Pull a rope and tension follows your effort. Cause and effect appear immediate and obvious, with no need to look deeper. Classical physics formalized this intuition without challenging it. Force became the central ingredient used to explain motion, and knowing the forces acting on an object was enough to predict how it would behave. Within this framework, force did not need an internal explanation. It was taken as a basic feature of nature. That approach achieved extraordinary success. Planetary orbits could be calculated with precision. Structures could be engineered to stand and endure. Mechanical systems behaved exactly as the equations predicted, and the world became mathematically navigable. Because of this success, the idea of force felt complete. There seemed to be no need to ask what force was made of. It worked, and working was enough. Yet this framework quietly relied on an assumption. Interaction could be treated as direct, even when no contact occurred. Gravity pulled across empty space, and magnetism acted without touching. The equations allowed it, so the mechanism was left unexamined. At large scales, this caused little trouble. Predictions remained accurate, and practical success concealed the missing structure. The absence of explanation did not interfere with calculation, so it went largely unnoticed. The limitation appeared only when physics began to look more closely. As measurements became more precise, the simplicity began to fray. Atoms refused to behave like miniature versions of familiar objects, and classical force laws stopped giving a stable picture. Electrons did not act like tiny solid balls. They did not orbit nuclei the way planets orbit stars. Applying classical force laws at this scale produced contradictions rather than clarity. The problem was not mathematical inconvenience, it was conceptual insufficiency. Force described how motion changed, but not how interaction actually occurred. Within the classical picture, space itself played no role. It was treated as an empty stage on which objects moved, while nothing between them mattered. All influence was assigned to the objects alone. Experiments at small scales showed that this could not be true. Behavior depended smoothly on distance in ways that could not be ignored. Something in the space between objects was clearly involved. Classical force had no language for this. It could assign a force after the fact, but it could not account for the structure that made interaction possible before contact. This marks the point where the classical idea reaches its limit, not because it is wrong, but because it stops explaining. It predicts outcomes without revealing the mechanism that produces them. Physics does not abandon successful ideas lightly. It extends them only when necessity demands it, and here that necessity is unavoidable. If interaction occurs reliably without contact, then something other than direct force must be responsible. Whatever replaces it must operate through space itself, and do so continuously. That requirement fixes the direction forward. The classical idea of force must give way to a framework in which space plays an active role. From that constraint, the next concept follows without choice. As attention moves to smaller scales, the classical picture begins to strain. Objects no longer behave like solid pieces meeting at a surface, and the idea of direct contact starts to lose its footing. Atoms, when examined closely, are mostly empty space. Their mass is concentrated in tiny regions, separated by distances that are enormous by comparison. If force required contact in the everyday sense, stability would be impossible at this scale. Yet atoms are stable. They hold their shape, form bonds, and assemble into larger structures that persist. Matter does not collapse inward or drift apart without cause. This persistence is not incidental. It is the central fact that demands explanation. That stability creates a precise contradiction. Components remain separated, yet they influence one another continuously. The classical explanation has nowhere left to stand. Experiments make this unavoidable. As particles approach one another, their behavior changes smoothly with distance. There is no sudden moment of impact, and no collision that can be identified as the cause of the response. Motion begins to adjust well before contact could occur. Resistance grows gradually rather than abruptly, and interaction unfolds as a function of separation itself. The response is already underway long before any notion of touching could apply. This rules out hidden impacts or delayed collisions. There is no missing instant where objects secretly meet. The behavior depends on distance in a continuous and repeatable way. At this scale, the space between objects matters. It cannot be ignored or treated as empty. Something in that region governs how particles behave as they move. The classical picture has no place for this. It treats space as passive, offering no contribution of its own, while assigning all action to the objects involved. Nature does not cooperate with that assumption. Measured behavior depends on what happens between particles, not just at their locations. The region separating them carries influence that directly affects motion. This is not an interpretive choice. It is forced by observation. If interaction varies smoothly with distance, then distance itself must participate in the mechanism. Once this is accepted, the failure becomes clear. Direct force cannot explain interaction without contact. It lacks the structure required to account for continuous, distance-dependent behavior. Importantly, this failure is constructive. It does not erase what came before. It identifies exactly where extension is required. Any replacement must meet specific demands. It must allow influence without contact. It must operate continuously through space. It must preserve causality and consistency. A framework that satisfies these conditions will naturally replace direct force at small scales. The shape of that framework is already implied by the problem itself. If space participates in interaction, then space must possess structure. That structure must exist everywhere, not just where particles sit. It must guide behavior locally and continuously. This requirement narrows the possibilities sharply. Only one concept satisfies all of it without contradiction. That concept is the field. Treating space as active changes the entire picture. If interaction depends on separation, then something must already exist between objects, shaping how they respond as they move. That something is not material in the usual sense. It has no edges, no surface, and no single location. Instead, it exists everywhere space exists, present even where no particles are found. Physics calls this a field. A field is not an object moving through space. It is a condition of space itself, defined at every point. Wherever you are, the field already has a value that specifies how motion would change if something were present there. This value is not abstract. It determines how matter behaves locally. Motion is guided before motion ever begins, because the conditions are already in place. With fields, interaction becomes local again. An object does not reach out to influence another across distance. It responds only to the field at its own position, and that response depends entirely on the structure of space where it is. As an object moves, it enters regions where the field is slightly different. Its motion adjusts accordingly, step by step, with cause and effect remaining tied together through space rather than jumping across it. This resolves the problem that direct force could not address. Influence no longer needs to leap across empty distance. Nothing acts where it is not present, and nothing responds without a local cause. Distance now plays a clear and natural role. The farther apart objects are, the more the field can change between them, and the weaker interaction becomes. That weakening is not imposed by rule. It follows from how field structure spreads through space. Fields also restore continuity. Because they vary smoothly from place to place, responses vary smoothly as well. Abrupt changes give way to gradual adjustment, governed by structure rather than impact. Importantly, fields exist even when nothing moves. They do not wait for particles to appear. They define possibilities in advance, and those possibilities remain whether or not they are realized. This makes fields physically real rather than mathematical convenience. A field can be calm or distorted, and that difference has measurable consequences. When a field is disturbed, something must account for the change. Altering structure is never free. Energy is involved whenever the field departs from its stable configuration. At this point, force takes on a different role. It is no longer fundamental. It becomes a description of how objects respond to field structure. Instead of saying an object feels a force, physics can say something more precise. The object moves the way it does because the field around it has a particular shape, and motion follows from conditions already present. This reframing is not cosmetic. It replaces mystery with mechanism and makes interaction something space itself participates in, rather than something imposed from elsewhere. The earlier problem is now resolved. Influence without contact no longer violates physical sense. Fields make such interaction inevitable. With fields established as real structures, the next step follows directly. If fields can vary and respond, then they must be able to carry physical quantities through space. Understanding what they carry and how they change leads naturally to the role of energy within fields. Calling something a field is only useful if it tells us what is physically present. At this stage, the field must do real work rather than serve as a convenient label. A field represents the state of space itself. At every location, space has properties that constrain what can happen there, and those properties exist whether or not anything is currently moving through them. This can be easier to sense than to define. Imagine walking across uneven ground at night. Your steps change because the ground changes beneath you, not because the ground reaches out to act on you. Fields play the same role for motion. They shape behavior locally. Objects respond to where they are, not to distant causes acting from elsewhere. This makes fields predictive rather than reactive. They do not wait for interaction to occur. They encode conditions in advance, specifying how motion would change if something were present. Because of this, fields carry information in a physical sense. They specify constraints on motion and change that are already in place before anything happens. The response is not decided in the moment, it is enforced by structure. This explains why force feels inevitable. When an object enters a region of space, its behavior is already determined by the field at that location. Nothing needs to choose what happens next. Fields also have measurable strength and direction. These are not abstractions. They can be mapped, compared, and tested, and they correspond directly to how motion responds. Where a field is stronger, motion changes more rapidly. Where it is weaker, motion changes gently. In every case, behavior follows structure without exception. That structure belongs to space rather than to the object. Removing the object does not remove the field. The field remains as a set of conditions waiting to be met. Because fields describe space itself, they must obey physical limits. They cannot change everywhere at once. Any alteration spreads gradually from place to place. This restores order to interaction. Cause travels through space rather than skipping over it, and every effect has a path that can be followed. At this level, force has almost disappeared as a primitive idea. What remains is response. Motion adjusts because space is shaped in a particular way. This reframing removes hidden mechanisms. There is no invisible hand pushing objects around. There is only structured space guiding behavior locally. The original difficulty is now resolved at a deeper level. Interaction without contact no longer requires special explanation. Fields make it unavoidable. One consequence follows directly. If fields are real physical structures, they must be able to change, and any change that matters must be accounted for physically. That accounting appears as energy. Understanding how fields store and move energy is the next necessary step, because without it, the picture remains incomplete. If a field can change, then that change must be accounted for physically. In nature, any change that has consequences carries energy with it, and fields are no exception. When a field is undisturbed, it occupies a stable configuration. Altering that configuration requires work, and that work does not disappear. It becomes energy stored in the structure of the field itself. This idea is not exotic. Stretching a spring stores energy in its shape, and releasing it allows that energy to reappear as motion. Fields behave in the same disciplined way, even though nothing solid is being stretched. When the structure of a field is distorted, energy resides in that distortion. The field retains the change until conditions allow it to relax, and during that time the stored energy remains physically real. This energy can be measured. It can be transferred from one region to another. It can reappear as motion, heat, or radiation. Nothing about it is symbolic or abstract. Introduce a charged particle into a region of space, and the surrounding field reshapes itself. That reshaping has an energy cost, which now resides in the field configuration rather than in the particle alone. Removing the particle does not automatically erase that stored energy. As the particle moves, the field must adjust again. Energy flows from one region of space to another as the structure updates, and that flow is carried by the field itself. Because energy moves, momentum moves as well. Fields do not merely guide objects passively. They participate actively in interaction by absorbing and delivering momentum in a way that preserves conservation laws. This participation explains a subtle but essential point. When one object accelerates another, the first object does not act alone. The field mediates the exchange so that energy and momentum remain balanced across the entire system. Nothing happens without accounting. Energy and momentum are never created or destroyed. Fields enforce these rules quietly and continuously, without exception. This also explains why interaction feels resistant. Distorting a field is not effortless. The field responds in proportion to how it is changed, and that response is what we experience as resistance. What we call force is closely tied to this resistance. It reflects how strongly a field resists being distorted and how that resistance redirects motion. Fields can also carry energy away from their source. When a field is disturbed rapidly, the change does not remain localized. It propagates outward as a traveling pattern through space. That traveling pattern carries energy with it and moves at a fixed speed set by the field's properties. Nothing outruns that limit, and nothing bypasses it. In some situations, this traveling energy escapes entirely as radiation. In others, it remains bound within the interaction, redistributing energy without loss. Both outcomes follow from the same field structure. At this point, fields are no longer passive scenery. They store energy, transport energy, and exchange energy with matter as part of a unified process. Force now appears as a consequence rather than a cause. Motion changes because energy is redistributed within fields, and behavior follows from how fields can be distorted and relaxed. This picture is coherent and complete at large. Scales. Energy stored in fields accounts for resistance, attraction, and repulsion in a continuous and lawful way. One further constraint remains. Energy in nature is not infinitely divisible. At sufficiently small scales, it appears only in fixed amounts. If fields carry energy, then fields must reflect that discreteness. Understanding how they do so leads directly into the quantum nature of fields. The idea that energy comes in fixed amounts forces a change in how fields are understood. If energy cannot be divided endlessly, then the structures that carry it cannot be perfectly smooth at all scales. This realization came from experiment rather than speculation. Atoms absorbed energy only in specific amounts, and they released it the same way. No smaller portions were ever detected, no matter how carefully measurements were made. Because fields are where energy is stored and transported, this discreteness must belong to fields themselves. A field can exist everywhere in space, but the energy it carries appears only in defined steps. Those steps are not optional, and nothing smaller ever appears. At large scales, this structure is easy to miss. Enormous numbers of tiny energy transfers overlap, and behavior looks continuous as a result. Smoothness emerges from quantity rather than from true continuity. At small scales, the structure reveals itself clearly. Energy changes occur in jumps rather than slides, and fields respond in packets rather than drifts. The underlying continuity of space remains, but the energy it carries does not vary freely. A helpful way to picture this is to think of a calm surface of water. From a distance, it looks unbroken and still. Up close, motion appears as individual ripples that rise and fall. The surface itself never disappears. Only its state changes. The ripples are not objects added to the water, but patterns that exist within it. Quantum fields behave in the same disciplined way. The field fills space continuously, defining conditions everywhere. Energy appears only through localized disturbances of that field. These disturbances are what we call particles. They are not tiny bits of material traveling through emptiness. They are organized excitations of an underlying field, carrying energy and momentum in discrete amounts. This shift is subtle but decisive. Particles stop being the foundation of reality, and fields take that role instead. What had once seemed like objects become patterns sustained by structure. An electron, in this picture, is no longer imagined as a solid point. It is a stable pattern in the electron field, and its properties arise from what that field allows. The same logic applies to light, where a photon is a traveling excitation of the electromagnetic field. This explains why particles of the same type are always identical. Every excitation of a given field must follow the same rules, so uniformity is enforced at the deepest level. It also explains why particles can appear and disappear. When energy enters a field, an excitation forms. When energy leaves, that excitation dissolves back into the field. Nothing mysterious is created or destroyed. Only the field's state changes. At this stage, force begins to look different again. It is no longer something acting between objects. It becomes something that happens within fields as energy is exchanged. When interactions occur, fields redistribute energy through their excitations, and motion changes as a result. Force is the name we give to that outcome. This picture resolves earlier tensions cleanly. Stability without contact, distance-dependent behavior, and conservation all follow from the same structure. Most importantly, matter and interaction are no longer separate categories. Both are expressions of field behavior, differing only in how long their excitations persist. With this structure in place, a further distinction becomes unavoidable. Some excitations form the matter that lasts. Others exist mainly to transfer influence. Understanding that distinction leads directly to force-carrying particles. Once fields take center stage, the meaning of a particle changes quietly but completely. What had once seemed like tiny objects becomes easier to understand as activity sustained by structure, rather than as substance moving through space. A particle is a localized pattern in a field. It is energy organized in a specific way, held together by the rules the field enforces. Nothing solid travels through emptiness in the classical sense. What persists is a pattern that the field allows to remain stable. This shift resolves a long-standing puzzle. Every electron behaves exactly like every other electron, no matter where it is found. That uniformity is difficult to justify if particles are independent objects with their own internal makeup. Within the field picture, uniformity becomes inevitable. All electrons are excitations of the same underlying field, and that field permits only one stable pattern of that type. Every excitation must therefore behave the same way. Persistence now comes from stability rather than material solidity. Some excitations settle into patterns that can last indefinitely under ordinary conditions. Those long-lived patterns make up what we call matter. Other excitations are brief. They appear during interactions and disappear once energy has been transferred. Their role is not to persist, but to mediate change within the field. This distinction matters deeply for understanding force. Forces do not require permanent particles traveling back and forth. They require temporary adjustments in field structure that redistribute energy and momentum. When two particles interact, the fields they inhabit cannot remain unchanged. Energy must be reallocated so that conservation laws continue to hold. That redistribution occurs through allowed excitations of the field itself. In this sense, interaction is carried out by the field rather than by the particles alone. Energy shifts from one pattern to another according to strict rules, and motion adjusts as a consequence. Force is no longer something added to particles from the outside. It is what motion looks like when fields exchange energy between their excitations. Because this exchange is quantized, interaction happens in steps. Each step is small, but never infinitely small. Perfectly smooth transfer does not exist at the deepest level. At everyday scales, these steps overlap in enormous numbers. The discreteness averages out, and force appears continuous and fluid. At small scales, individual exchanges matter. Single excitations can alter outcomes, and probability enters without contradiction. Nothing in this picture is arbitrary. The field dictates which excitations are allowed, and those allowances determine how particles behave and how forces arise. Matter and interaction are no longer separate categories. They are two expressions of the same underlying structure, differing only in how energy is arranged and how long that arrangement lasts. This realization simplifies the framework rather than complicating it. There is one underlying description instead of two, and fields govern everything that happens. With this understanding in place, another distinction becomes unavoidable. Some excitations mainly form matter. Others exist primarily to transmit interaction itself. Those interaction-focused excitations complete the picture of how force is carried. At this point, interaction requires a dedicated mechanism. If fields exchange energy through excitations, then some of those excitations must exist primarily to carry influence rather than to remain as matter. This is where force-carrying particles enter the picture. Not every excitation of a field is meant to last. Some patterns are stable and persistent, forming electrons, quarks, and atoms. Other patterns are fleeting, appearing only while interaction is taking place, and disappearing once their role is complete. These short-lived excitations are not defects or leftovers. They are built into the structure of the field itself, and their role is specific. Whenever energy and momentum must be transferred between particles, the field must change, and that change requires a carrier. Force-carrying particles are those carriers. They are not little objects launched from one particle to another. They are temporary reorganizations of the field that move through space according to strict rules. Their existence is defined by what the field permits, not by any mechanical picture we might imagine. The electromagnetic field provides the clearest example. When charged particles interact, the field between them cannot remain static. Energy and momentum must be redistributed so that conservation laws continue to hold. The electromagnetic field allows a specific kind of excitation to do this work. That excitation is the photon. In some situations, photons escape the interaction entirely. They travel freely, through space as light, and can be detected directly. In other situations, the exchange remains internal to the interaction, with no radiation emitted. Both outcomes follow from the same structure. What differs is whether the excitation becomes independent or remains bound to the interaction. The field determines this behavior through its constraints. This distinction matters because it shows that force does not require emission. Interaction can occur without energy being radiated away. Energy can be exchanged internally, while the total remains unchanged. Other forces follow the same logic. Each fundamental interaction corresponds to a field, and each such field permits specific excitations that carry influence. The strong nuclear force uses its own carriers. The weak nuclear force relies on heavier ones. The pattern remains the same even as the details differ. These force-carrying particles behave differently from matter particles. They are often unstable when isolated, and may exist only briefly, sometimes only within exchange itself. Their properties determine how forces behave. The mass of the carrier affects how far influence can reach. Heavier carriers limit interaction to short distances, while lighter or massless carriers allow influence to extend further. This explains why some forces are long-ranged and others are confined. Electromagnetism extends far because its carrier is massless. The strong force remains tightly bound because its carriers cannot travel freely. Nothing in this picture is added by hand. These features follow directly from field structure. Once the field is specified, its allowed excitations determine how interaction proceeds. Force now has a clearer physical identity. It is not a push, not a substance, and not an abstract command. It is the visible outcome of energy and momentum being exchanged through permitted excitations of a field. With force-carrying particles in place, interaction no longer needs to be assumed. It has a mechanism that operates consistently and without exception. One further step remains. Understanding how these exchanges produce attraction and repulsion requires looking more closely at the exchange process itself. That mechanism follows directly from the structure already in place. With force-carrying particles established, interaction can be described as a process rather than as an outcome. Motion does not change because something reaches across space. It changes because energy and momentum are exchanged in a controlled way. Consider two charged particles placed near one another. Each exists within the electromagnetic field, and that field already has a particular structure shaped by their presence. The configuration cannot remain static once either particle moves. When one particle shifts position, the surrounding field must adjust. That adjustment begins locally and then spreads outward through space. It does not occur everywhere at once because physical change never happens instantaneously. As the field updates, it carries energy and momentum with it. This transport takes the form of a permitted excitation, which exists because conservation laws require a carrier for the exchange. The excitation is not optional. It is demanded by structure. When the field change reaches the second particle, the conditions at that location are no longer the same. The particle responds to its local field configuration, and its motion changes accordingly. Momentum has been exchanged, and energy has been redistributed. Attraction and repulsion arise from this same process. They are not separate mechanisms or special cases. The difference lies in how the field is configured and how the exchange unfolds. If the exchange shifts momentum toward another particle, the motion appears attractive. If the shift is away, the motion appears repulsive. The field determines the direction without ambiguity or choice. This explains why forces are always reciprocal. When one particle changes motion, the other must as well. The field enforces balance so that momentum is conserved across the interaction. Distance enters naturally into this picture. As separation increases, the field change spreads across a larger region of space. Exchange becomes weaker because energy is distributed more broadly, not because influence fades arbitrarily. No additional rule is required to explain this weakening. The structure of the field guarantees it. Influence declines because exchange becomes less concentrated as it propagates. Time also falls into place. Effects do not arrive before causes. every adjustment takes time to propagate through the field, and no response occurs before the necessary information arrives. This preserves causality without exception. Nothing acts where it has not yet arrived, and every response remains local and lawful. Because exchange happens in discrete steps, force is quantized at its foundation. There is no infinitely gentle nudge at the deepest level. Only allowed transfers ever occur. At large scales, countless exchanges overlap. Individual steps blur together, and force appears smooth and continuous. At small scales, each exchange matters. Outcomes depend on probabilities rather than certainties, and quantum behavior emerges naturally from the same rules. This exchange picture removes the last trace of mystery from force. Motion changes because energy and momentum move through fields, and fields move energy through permitted excitations. Force is no longer a primitive ingredient of nature. It is the visible consequence of structured exchange. Interaction is a process, not a push. With this mechanism in place, one subtle element remains to be clarified. Some exchanges do not involve particles that can ever be observed directly. They occur entirely within the interaction itself, and understanding them completes the picture. The exchange mechanism is almost complete, but one refinement brings it into sharper focus. Not every exchange produces a particle that can exist independently in space. Some transfers occur entirely within the interaction itself and never appear as observable particles. These internal carriers are known as virtual particles. The term can be misleading if taken casually. Virtual does not mean imaginary or optional. It means constrained. These excitations exist only under the conditions of the exchange, and only for as long as the interaction requires. When two particles interact, the field between them must reorganize in order to transfer energy and momentum. That reorganization demands a carrier, but it does not require that the carrier persist or escape as a free particle. The exchange occurs within tight limits and then resolves. Virtual particles represent those constrained excitations. They exist only as part of the interaction process itself. Their properties are determined by what the field allows during exchange, not by what can later be detected in isolation. This explains why virtual particles are never observed directly. They are not meant to be isolated. They appear and disappear within the accounting of interaction, leaving behind only their effects on motion and energy distribution. Despite their invisibility, those effects are precise. Virtual particles determine how strong a force is, how quickly it weakens with distance, and how momentum is shared between interacting systems. In electromagnetic interactions, the exchange involves virtual photons. These photons do not travel freely through space as light. They remain bound to the interaction, carrying momentum without radiating energy away. This allows static forces to exist. A charged particle can exert influence without losing energy, because the exchange remains internal to the field structure. The field reorganizes, and balance is preserved. The same pattern appears in other forces. The strong nuclear force relies on virtual gluons to bind quarks together. The weak nuclear force uses heavy virtual carriers to mediate particle transformations. In each case, the mass of the carrier matters. Heavier virtual particles can exist only briefly, which limits how far the exchange can reach. Range becomes a direct consequence of field constraints rather than an added rule. This is why some forces act only over extremely short distances. The field allows exchange, but only within strict spatial limits. Structure sets the boundary without exception. Virtual particles also preserve conservation laws. Energy and momentum balance out over the full interaction, even if temporary deviations appear during the exchange. Those deviations are allowed only within carefully constrained limits. Nothing here violates physical rules. The field never loses track of accounting. Every exchange closes cleanly and consistently. This completes the internal mechanism of force. Fields exist everywhere. Energy is carried in discrete excitations. Exchange redistributes that energy under constraint. Force now has a complete description. It is not a substance filling space. It is not a mysterious pull acting at a distance. It is regulated interaction governed by field structure. With this mechanism clarified, one consequence remains to be addressed explicitly. Forces act across distance without contact, yet never violate locality. Understanding why this works so cleanly ties the picture together. By this point, distance no longer threatens the explanation. Interaction does not depend on objects meeting, because contact was never doing the work in the first place. Forces act across space because fields already occupy that space. Every object exists within a field, and every field has structure at each location. Nothing needs to travel instantly from one object to another. When a particle changes position or motion, the surrounding field must adjust. That adjustment begins locally at the particle's position and then spreads outward through space. The update unfolds step by step, not all at once. This gradual propagation is essential. It prevents influence from skipping over space and preserves the order of cause and effect. Each region updates only after the change has reached it. As the field changes, it carries energy and momentum with it. Those changes move through space region by region, reshaping conditions as they go. The field itself performs the mediation. When another particle lies along this path, it encounters a new local field configuration. Its response is immediate and local. Nothing distant reaches out to affect it directly. This is why forces do not violate locality. Every response happens where the particle is. The field delivers information in sequence, and particles respond only to what has arrived. Distance simply determines how the field behaves along the way. As separation increases, the field change spreads across more space. Energy becomes less concentrated, and interaction weakens as a natural result. No additional rule is required to explain this weakening. Force fades with distance because the field must distribute influence as it propagates. Geometry and structure enforce the decline. Timing follows the same logic. A change cannot be felt before it arrives. Propagation speed limits how quickly influence can travel, and those limits are never bypassed. This preserves relativity without compromise. No signal outruns the structure that carries it, and no interaction escapes the constraints of space and time. The earlier mystery of action at a distance now dissolves. Nothing acts where it is not present. Nothing responds before it is informed. Instead, space itself becomes the mediator. Fields fill it. Changes move through it. Objects respond locally to the conditions that arrive. This picture is disciplined and complete. It allows long-range interaction without shortcuts, and it allows distance to matter without breaking causality. At this point, the original concern has been fully resolved. Force does not leap across emptiness. It unfolds through structured space, step by step. With that understanding secured, one example stands out as especially transparent. One force displays every part of this mechanism in a way that can be tested directly. That force is electromagnetism. Among all known forces, electromagnetism reveals the underlying structure with unusual clarity. It is familiar enough to feel ordinary, yet precise enough to expose every part of the mechanism at work. Electric charge exists within the electromagnetic field at all times. That field fills space completely, even in regions where no charges are present. Its structure already specifies how motion would change if a charged particle were placed there. A stationary charge shapes the surrounding field in a stable way. Influence exists even when nothing moves, because the conditions for interaction are already established in space. Introduce a second charge, and the situation reorganizes. The field adjusts to accommodate both sources, redistributing energy and momentum as required. Each charge responds only to the field at its own position, and motion follows from those local conditions. Attraction or repulsion emerges immediately from this structure. Opposite charges move together, while like charges move apart. The direction of motion is determined by the field's configuration rather than by any instruction passed between particles. When a charge begins to move, the field cannot remain static. Its configuration must update to reflect the new motion, and that update spreads outward through space at a fixed speed. Nothing about this process is instantaneous or arbitrary. The spreading change carries energy and momentum. In quantum terms, it appears as an excitation of the electromagnetic field. That excitation is known as a photon. In some cases, photons escape the interaction entirely. They travel freely through space as light and can be detected directly. In other cases, the exchange remains confined to the interaction with no radiation emitted. Static forces belong to this second category. Charges can influence one another without losing energy, because the exchange occurs internally within the field. Virtual photons handle the redistribution, while the total energy remains constant. This dual behavior is especially revealing. Radiation and force are not separate phenomena layered on top of one another. They are different outcomes supported by the same field structure, depending on how energy is exchanged. Range becomes transparent in this context. Because photons are massless, electromagnetic influence can extend across vast distances. Nothing in the field restricts how far exchange can occur. Strength, however, still fades with separation. As distance increases, energy spreads across a larger region of space, and interaction weakens. The field's geometry enforces this decline without additional rules. Quantization is equally evident here. Charge comes in fixed units, and field excitations do as well. Interaction proceeds through discrete exchanges even when the resulting behavior appears smooth. At large scales, these exchanges overlap in enormous numbers. Individual steps blur together, and classical laws emerge as reliable approximations. At small scales, discreteness matters, and individual exchanges can alter outcomes. Electromagnetism does not introduce new principles, it makes existing ones visible. By examining it closely, the field-based picture becomes difficult to avoid rather than merely plausible. With this clarity in place, other forces no longer appear mysterious. They become variations in field behavior rather than fundamentally different kinds of interaction. Some bind matter tightly at extremely small distances. Others operate briefly and then fade. Each difference reflects field properties rather than new rules. The next example makes this especially clear. That example is the strong nuclear force. Electromagnetism feels familiar in part because its influence reaches far beyond its source. The strong nuclear force behaves very differently, even though it follows the same underlying field-based logic. Inside an atomic nucleus, protons sit extremely close together. Each carries positive electric charge, which means electromagnetic repulsion should push them apart. Yet nuclei remain bound and stable under ordinary conditions. This stability is not accidental. A different field operates at these tiny distances, one that overwhelms electromagnetic repulsion when particles are close enough to feel its influence. The strong force acts only within a narrow range. Beyond that range, its influence drops off rapidly. Inside it, the force becomes dominant, binding particles together with extraordinary strength. Quarks, the fundamental components of protons and neutrons, exist within a strong force field. That field has its own structure and its own permitted excitations, which are known as gluons. Gluons function as carriers of interaction in much the same way photons do for electromagnetism. The crucial difference lies in how the strong field behaves when it is disturbed. Unlike the electromagnetic field, the strong field does not weaken as its sources are pulled apart. Instead, resistance increases. Pulling quarks apart requires more and more energy because the field resists separation rather than relaxing under it. The farther the separation, the stronger the restoring influence becomes. This behavior has a striking consequence. Quarks are never found alone. They remain permanently confined within larger particles, not because of an added rule, but because the field structure makes isolation energetically impossible. When enough energy is applied, the field reorganizes rather than allowing separation. New particles form from the energy supplied, and confinement remains intact. The field enforces stability by reshaping itself. Within the nucleus, this same interaction operates between protons and neutrons. Gluon-mediated exchange keeps these particles bound despite their electromagnetic repulsion. Balance is maintained because the strong field dominates at very short distances. Range matters here in a precise way. The strong force does not extend far into space. Its influence is powerful but tightly localized, and it fades rapidly beyond the scale of the nucleus. This explains why nuclei have well-defined sizes. Beyond a certain distance, the strong field no longer binds particles together, and nuclear structure comes to an end where the fields reach ends. Nothing about this force violates the framework established earlier. Fields still govern interaction. Energy still moves through permitted excitations. Exchange still enforces conservation laws. What changes is the behavior of the field itself. The strong field responds differently to separation, and its excitations interact with one another, rather than remaining independent. Gluons can influence other gluons. The field becomes self-interacting, adding complexity without introducing new principles. The same rules apply, but their consequences are amplified. The strong force demonstrates how varied outcomes can arise from a shared foundation. By altering field properties, nature produces radically different behavior while preserving the same underlying structure. With this example, the field-based picture gains depth. It accounts for binding, confinement, and stability at the smallest scales without requiring additional mechanisms. One force remains to be considered that behaves differently again. Its reach is short, its effects are subtle, and its role is transformation rather than binding. That force is the weak nuclear force. The weak nuclear force enters the picture quietly. It does not bind matter into stable structures, and it does not reach across space in an obvious way. Its presence is revealed through change rather than through cohesion. This force operates over extremely short distances. Beyond those limits, its influence effectively disappears. Within them, however, it governs some of the most important transformations in nature. Radioactive decay provides a clear example. A particle changes identity, releasing energy and rearranging matter in the process. Nothing is pushed or pulled in the everyday sense, yet a fundamental interaction is at work. The weak force is responsible for these transformations. It allows one type of particle to become another, enabling processes that would otherwise be forbidden. Without it, many reactions essential to the universe would never occur. As with the other forces, this behavior arises from an underlying field. The weak field fills space just as other fields do, even though its effects are rarely noticed at large scales. Its influence becomes apparent only under specific conditions. The carriers of the weak interaction are unusual. They are far heavier than photons or gluons, and that mass has decisive consequences for how the interaction behaves. Because these carriers are heavy, they can exist only briefly. The field permits exchange for a very short time before suppressing it. As a result, the influence of the weak force fades almost immediately with distance. This explains the short range of the weak interaction without additional assumptions. The field allows exchange, but only within a narrow spatial window. Structure sets the boundary automatically. Despite its limited reach, the weak force plays a decisive role. It governs radioactive decay, drives key reactions in stars, and shapes how matter evolves over time. Subtlety does not imply insignificance. The mechanism itself is now familiar. Energy and momentum are exchanged through permitted excitations of the field. What differs is how constrained those excitations are. Because exchange is brief, the effects appear sudden. Particles decay rather than drift. Transformation replaces gradual motion as the dominant outcome. Nothing here breaks the established framework. Fields still mediate interaction. Excitations still carry exchange. Constraints still determine behavior. The weak force shows that force does not always produce motion through space. Sometimes it produces change in identity. Both outcomes arise from the same underlying structure. With this, 3 fundamental interactions have been examined in detail. Each behaves differently, yet each follows the same field-based logic. One interaction remains that does not yet fit cleanly into this picture. Its effects are familiar, but its quantum description is incomplete. Understanding why clarifies the limits of current knowledge. That interaction is gravity. Gravity feels more familiar than any other interaction, yet it resists the framework that works so well elsewhere. We experience it constantly as weight, fall, and orbit, and its effects can be described with extraordinary accuracy at large scales. Planets move along predictable paths. Galaxies form stable structures. Space-time itself behaves in ways that can be calculated and tested. In this domain, gravity is one of the most precisely measured features of nature. Classical physics describes gravity in a way that already departs from the idea of force as push or pull. Instead of acting through exchange particles in the usual sense, gravity appears as curvature in space-time. Mass and energy shape geometry, and motion follows that shape. Objects fall not because they are pulled downward by an invisible influence, but because they move along paths determined by curved space-time. This description is elegant, coherent, and deeply successful wherever it applies. Quantum physics approaches interaction differently. It explains forces through fields, excitations, and discrete exchanges, and it does so with remarkable success for electromagnetism and the nuclear forces. When gravity is brought into this framework, however, the pieces no longer fit together cleanly. The difficulty is not observational. Gravity behaves exactly as expected across enormous distances. The problem is structural. In gravity, space-time itself becomes the field, and quantizing that structure introduces conflicts with the assumptions quantum theory relies on. Smooth geometry does not break easily into discrete excitations. Attempts to treat space-time the way other fields are treated lead to mathematical inconsistencies and loss of predictability at extreme scales. Physicists can describe weak gravitational interactions using quantum ideas, and those descriptions work well in limited regimes. At extremes, such as near black holes or at the beginning of the universe, the classical picture and the quantum picture no longer agree. Each framework remains valid within its own domain. Classical gravity describes large-scale structure with precision. Quantum field theory describes particle interactions with equal success. What is missing is a single description that fully unites them. This does not mean gravity violates the principles seen elsewhere. It still respects locality, causality, and conservation. What remains incomplete is the account of how gravitational interaction fits into the same exchange-based structure that explains other forces. The gravitational field is present, its effects are real and measurable. What is not yet fully understood is how that field behaves at the smallest scales, where quantum effects dominate. Importantly, this gap does not undermine what has already been established. For 3 of the 4 fundamental interactions, force is made of structured exchange within quantum fields, mediated by permitted excitations and constrained by conservation laws. Gravity stands apart, not because it contradicts this picture, but because its quantum version is unfinished. It marks a frontier rather than a flaw. With gravity placed in context, the overall structure becomes clearer rather than weaker. Most forces are already explained as regulated interaction within fields, and the remaining one highlights how much of the universe has already yielded to that understanding. From here, the picture can widen without reopening earlier questions. What force is made of has been established where physics is complete, and that foundation allows a final perspective to emerge. With gravity placed at the boundary of current understanding, a broader pattern comes into focus. Across the forces that are well described, force no longer appears as a push, a pull, or a substance acting between objects. It appears instead as a regulated transfer of information through fields. Whenever a particle changes position, accelerates, or alters its state, the surrounding field cannot remain unchanged. The structure of the field records that change immediately at the particle's location. This record is not symbolic or abstract. It is a physical alteration of the conditions in space. From that point, the information spreads. The field updates itself outward, region by region, carrying with it the details of what has changed. Energy and momentum move as part of this update, but just as important is the information about how nearby systems must now behave. A second particle does not experience a distant object acting on it directly. Instead, it encounters a field that has already been shaped by prior events. Its response is local and automatic, governed by the information embedded in the field at that location. Motion changes because conditions have changed, not because a command has been issued. Seen this way, force becomes inseparable from communication. Fields communicate changes in energy and momentum across space, and matter responds according to strict rules. There is no interpretation involved. The field does not suggest what might happen. It specifies what must happen. This perspective unifies ideas that once seemed separate. Exchange, causality, and conservation all become aspects of the same physical process. Information flows through fields in ways that preserve balance and order, and force is the macroscopic trace left by that flow. Importantly, this information is physical. It is not knowledge or awareness. It is structure. When a field carries information, its configuration encodes constraints on motion and change, and those constraints are enforced wherever the information arrives. This explains why force feels directional. Information in a field does not spread uniformly. It propagates along paths determined by geometry and field properties. Attraction and repulsion arise because information reshapes local conditions in specific ways that guide motion. It also explains why force is reliable. Information transfer through fields follows fixed laws. Given the same conditions, the same information propagates in the same way, and the same responses follow. Once structure is set, behavior does not vary. Thinking in terms of information also clarifies why force is never instantaneous. Information takes time to propagate. A field must update itself continuously, and those updates cannot skip space. Every response has a history that can be traced through the field's evolution. This view removes the last temptation to imagine hidden mechanisms. Nothing travels secretly between particles. Nothing reaches across space outside the rules. The field carries information forward, and systems respond when that information arrives. At large scales, this process becomes difficult to notice. Information flows densely and continuously, so effects appear smooth and immediate. At small scales, individual updates matter, and behavior becomes sensitive to discrete exchanges. The underlying process remains the same. Force, in this sense, is not a primitive ingredient added to matter. It is the outward sign that information is moving through structured space. Motion changes because the universe keeps track of itself and enforces its own constraints. This understanding does not weaken the idea of force, it strengthens it. By tying force to information transfer, physics arrives at a description that is precise, local, and compatible with everything else that governs the universe. With this view established, one final constraint must be made explicit. Information cannot travel arbitrarily fast. The way force operates must respect the limits imposed by space and time themselves. Once force is understood as the transfer of information through fields, a firm boundary comes into view. Information cannot move freely or instantaneously. The universe enforces limits, and those limits apply to every interaction without exception. Relativity establishes this constraint with precision. It states that no physical influence can propagate faster than a fixed maximum speed. This limit is not reserved for signals or messages alone. It applies to every change that can have physical consequences, including the updates carried by fields. When a particle accelerates, the field around it changes first at that location. That change does not immediately reshape distant regions of space. Instead, it begins a process of propagation that unfolds gradually, spreading outward step by step. Each region updates only after the change has reached it. This ensures that cause always precedes effect. A particle cannot respond to an event that has not yet arrived through the field that connects them. At human scales, this delay is difficult to notice. Distances are small, and propagation is fast. The interaction feels immediate, even though it is not. At microscopic scales, delays become measurable. At cosmic scales, they become decisive. This constraint is essential for coherence. Without it, different observers could disagree about the order of events in ways that would break consistency. Relativity preserves a shared structure of cause and effect by enforcing a universal speed limit on information transfer. Fields automatically respect this limit. Their behavior does not allow instant updates or shortcuts through space. Any disturbance, no matter how small, propagates at a finite speed determined by the field's properties. Force therefore cannot act instantaneously, even in principle. The feeling of immediacy arises from scale, not from exception. Every interaction unfolds in time as well as space. This perspective also clarifies why forces weaken with distance. As information propagates outward, it spreads across larger regions of space. The structure of the field distributes the change, reducing its intensity as separation grows. Distance is not an obstacle added afterward. It is built into how propagation works. The geometry of space and the limits on speed together determine how influence fades. Relativity also protects locality. A particle responds only to what happens in its immediate surroundings. It does not need access to distant causes. All that matters is the local field configuration it encounters. This reinforces the field-based picture of force. There is no central authority issuing commands across space. Fields evolve according to fixed laws, and particles respond locally to those evolving conditions. Importantly, relativity does not compete with the quantum description of force. Where both apply, they align. Quantum fields propagate information in ways that respect relativistic limits, ensuring that no exchange violates causality. Where difficulties arise, such as in attempts to unify gravity with quantum theory, they appear precisely at the intersection of these constraints. The challenge highlights how fundamental the limits are, not how fragile the framework is. By imposing strict speed limits on information, relativity gives force its temporal structure. Interactions take time. Influence arrives in sequence. The universe unfolds in an ordered way. even when behavior appears probabilistic at small scales. This completes another essential part of the picture. Force is not only structured exchange, it is exchange that unfolds within space and time, bound by limits that apply everywhere without exception. With these constraints made explicit, the final clarification becomes possible. Understanding what force is also requires understanding what it is not. With the structure now firmly in place, it becomes possible to remove ideas that no longer belong. Clarifying what force is not made of is not a detour. It is a necessary tightening of the picture, because older intuitions can quietly distort an otherwise precise explanation. Force is not a substance that flows between objects. Nothing material streams from one particle to another when interaction occurs. There is no invisible fluid filling space and pressing on matter. If such a substance existed, it would need its own dynamics and conservation laws, and no evidence for any of this appears in experiment. Force is also not an object in transit. Nothing is thrown across space to make something move. Even force-carrying particles are not projectiles in the everyday sense. They are temporary excitations of fields, constrained by rules that prevent them from behaving like independent objects unless conditions allow it. Equally important, force is not a command or instruction issued by one object to another. Particles do not tell each other how to move. There is no hidden signaling layer where decisions are made. Motion changes because local conditions change, not because something elsewhere demands compliance. Force is not stored inside particles as a hidden property waiting to be released. Particles do not carry force around with them. What they carry are properties such as charge or mass, which shape the surrounding field. Interaction arises from the field's response, not from anything residing inside the particle itself. It is also misleading to think of force as something added on top of motion. Motion does not exist first, with force applied afterward as an external modifier. Motion evolves as it does because the field structure already constrains what is allowed at every moment. Force is not arbitrary. It does not fluctuate according to circumstance or interpretation. Given the same field configuration and the same initial conditions, the same interaction will occur. Once structure is defined, behavior is fixed. Another intuition to discard is the idea that force exists independently of space. Interaction cannot be separated from the spatial structure in which it unfolds. Remove the field, and there is no force left behind. What remains is simply the absence of interaction. Force is also not a placeholder for ignorance. It is not a word used to mask missing explanation. In the quantum field picture, force has a mechanism, constraints, and measurable consequences wherever the framework applies. Removing these misconceptions does not make force less real. It makes it more precise. By letting go of images that no longer match how nature behaves, the explanation becomes simpler rather than more abstract. What remains after this removal is coherent and minimal. Fields exist. They carry energy and momentum. They propagate information according to strict limits. Matter responds locally to the conditions those fields create. Force emerges from this process without additional ingredients. This clarity also prevents confusion across scales. At everyday distances, force can still be described as push and pull because the underlying structure averages out. At small scales, the same structure reveals itself as exchange and propagation. The description changes, but the mechanism does not. Understanding what force is not made of protects the explanation from slipping backward into older metaphors. It keeps the narrative moving forward towards synthesis, rather than circling familiar but inaccurate images. With misconceptions set aside, the remaining picture stands on its own. Force no longer needs analogy to substance, intent, or contact. It stands as a consequence of structure and constraint. Only one step remains. Having clarified what force is not, the final task is to state clearly what force is, in its most complete and stable form. With every component now in place, the answer can settle without strain. According to quantum physics, force is not something added to the universe. It is a pattern that emerges when the universe enforces its own structure. Fields form the foundation. They exist everywhere, whether or not particles are present, and they define local conditions that constrain what can happen. When those conditions change, the change is physical. Energy and momentum are redistributed, and information about that redistribution propagates through space. Particles are expressions of this structure rather than exceptions to it. They are stable or transient excitations of fields, allowed patterns that carry energy in discrete amounts. Some persist and form matter. Others exist briefly to mediate interaction. Together, they give fields a way to express change. Force arises when these elements interact. As fields exchange energy and momentum through permitted excitations, motion adjusts in response to local conditions. What we call force is the visible imprint of that adjustment. It is the name given to how motion evolves when structure demands it. Nothing in this process is optional or improvised. Conservation laws hold because the field enforces them. Causality holds because changes propagate step by step. Limits on speed hold because information cannot outrun the structure that carries it. Every feature of force follows from constraint rather than assumption. This view also explains why force feels so fundamental in everyday life. At large scales, countless microscopic exchanges overlap, and the underlying discreteness fades from view. The result is smooth, predictable behavior that can be described with simple laws. The simplicity is real, but it is emergent rather than basic. At small scales, the same process reveals its texture. Individual exchanges matter. Probabilities replace certainties. Behavior becomes sensitive to discrete events. The underlying rules, however, do not change. Understanding force this way removes the need for hidden mechanisms. There is no substance flowing unseen, no command issued across space, and no mysterious contact where none exists. There is only structure, propagation, and response. This synthesis also explains why different forces behave so differently. Electromagnetism, the strong force, and the weak force all arise from fields with distinct properties. Their ranges, strengths, and effects differ because their structures differ, not because the principles change. Gravity stands apart only because its quantum description remains unfinished. Its classical behavior already fits the idea of structured space-guiding motion. What remains open is how that structure behaves at the smallest scales. The gap marks a frontier, not a contradiction. By the time this picture is complete, the original question no longer feels open. Force is made of regulated exchange within fields. It is the consequence of energy and momentum moving under constraint. This answer does not diminish the universe, it deepens it. Force becomes not an external influence acting on matter, but an expression of how the universe maintains coherence as things change. In the end, force is how order is preserved through motion. It is not something the universe uses, it is something the universe is doing.